So what is the data structure that I went over? Anyone want to tell me? Stack. Right? Stack. So stack is what we call a what in, what out data structure. Anybody remember? Last in, first out, or LIFO for short. Last in, first out, meaning that it is that the way a stack works is the last thing that goes into the stack is the first thing that comes out of the stack, which sounds really abstract, but honestly, just imagine like you've got a stack, we've got a plate here, and we've got a stack of delicious pancakes just stacked one on top of another, right? Stacks and queues, which is the other data structure we learned, they are actually really well named. War of 100 Years, terribly named, right? 7 Years War, terribly named. Stacks and queues, historians have a horrible track record when it comes to naming things. Stacks and queues, on the other hand, we pretty much nailed that one. So stacks are essentially really easy versions of linked lists, where basically all you can do is manipulate the head of the list, which we'll call the top of the stack, just for simplicity's sake, right? You can either put items on top of the stack. You can remove items from the top. You can remove one item at a time from the top of the stack. You can put one item at a time on the top of the stack. You can look at what the top item of the stack is, and that is it. The only other operation you can do, you can't even check the size, right? If you've watched the video, you notice you can't even check the size. The only thing you can do is ask, is the stack empty or not, right? So 4 operations, which we call push, which pushes an item onto the stack, pop, which takes an item off of the stack, peek, which looks at the top of the stack. And by the way, if you need to get the item back, you can just pop it off. Essentially, this is get and remove, and this is just get, but don't remove the top item, right? So if you just want to check what the top item is, you use this. If you want to remove it and possibly get it back, use this, right? So add, remove, check the top, and then you don't even check this. You don't even keep track of the size. You just use empty. You can use now. You can. I demonstrated how to build this thing with a linked list, but you can totally use an array or array list based structure for this. It works either way. With the queue, I'll demonstrate how to use something called a circular array, but again, that's just more relevant for the queue. And those videos are upcoming, but they weren't necessary for the homework, so why bombard you with that? But they'll be coming later this week, and eventually, and you should be able to, and there'll be a quiz on them, but I'll let you know, and obviously they'll come after the videos. The stack, though, is what you need for your homework. Now, what the stack is great for is essentially when we need to reverse things, as you may have seen in the example. They're also good for basically keeping a very basic form of memory in the computer. And I'll come back to that point. But the other thing that you'll see for the homework is they're good for backtracking. Now, as far as memory is concerned, right, I mentioned that regular languages and regular expressions in one video don't cut it for some of the problems that you might need a stack for. The idea here is that you can build there's a 4,000 level class that we don't offer too often called Automata. And what we talk about is essentially that there's these things called discrete finite automata, okay, which are essentially state machines, as we call them. Essentially, you can go from one state to another state to another state. So, for instance, if you wanted to build a machine that, a state machine that matched this regular expression, A followed by, let's see, NA followed by at least one B followed by another A. That's the regular expression for finding at least one B, right? So we have our starting position. We'd have an A here to indicate that we transition to this next state, followed by a B to show that we've seen one B. And then at this third state, we can either say we found another B, so we wrap back around ourselves, and then we go to another, or we can find an A and we go to that. So as you can see, this is the lines that you would follow from basically that would find a state machine. Sorry, you'd follow this as a diagram for a state machine if you wanted to go between the state of of reading a string and then reading a string that had matched this pattern, right? And if you were able to get to the finished state, then you knew you found this pattern. And otherwise, if you found an invalid input, you would know that you couldn't do this pattern. It's a bit high level. That's okay. The idea here is, though, that this thing has no memory, but these things map to regular languages and your regular expression. These are equivalent. You can build anything like this into a regular expression. But they have no memory. The next level of a state machine is to add one stack. Okay, to add one stack that we can put items in and pop items out of. Okay? So, and this gives us some rudimentary memory, and this gives us context-free grammars and the like. Add one more stack, and we kind of cheat at the way we present this then. Right? If you add two stacks, then we cheat at the way we present this. Instead, we just look at the stack itself. We lay the stack sideways, and we say basically there's this stack, and then there's this stack laid the other way, and then there's this position in the middle that we're currently looking at, right? And this position is either marked, and what we say is that, well, now we have the stack, we can imagine a line of infinite size, of like ticker tape was kind of the way they were thinking, right? Imagine this ticker tape line, right? That either you can mark on the ticker tape or unmark it, right? Just these little squares that you can, and then you can essentially push this onto a stack and pull from the other, and pop from the other stack to get the next location if you want to move right along the line, or push this onto the other side and pull from this side if you want to move left on the ticker tape. Okay, so that's very basic operations. So this is a line of infinite length. We can mark it or unmark it, give it a 0 or 1, right? Move back and forth between that, and suddenly we have a mathematical model for a computer, which we call Turing languages. So you can use this to create a Turing complete language or a Turing machine. So two stacks essentially. So if you take a state machine, add one stack, you get one type of language. Add a second stack, you get this thing called a Turing machine, which allows us to basically do any kind of operation that we want, and start proving what we can and can't do with the computer. So stacks, despite being very simple, if you have two of them, you can essentially do anything you need to, which is interesting and profound. That something so simple has that implication. What we are going to do with them, though, if you haven't taken a look at the homework, is that we are going to use them to solve mazes. Because stacks are amazingly good at backtracking, right? You keep track of your last known location. Your last known location is at the top of the stack. Sorry. No. More sources. Auxiliary HDMI. Right, you keep track of your sources on the stack, and if you hit a dead end, you backtrack. So I put up a video on this, but let's see, teaching, destruct, assignments, stack maze. Right, so maze.java. Right, so I've given you this maze program, right, and I'm currently loading this with my solution, but it will create a maze for you. And then we can run it, and it solves a maze. And your solution will look something like this. Now, what I do is that if this is the first time you see it, don't be too alarmed. The code I give you amounts to this, which is just without the solution on here. So if I recompile it, F8, F5, it will give you this, which is the entire maze just without the solution. So all the graphical stuff is already taken care of. And the only thing you have to learn about graphics is something which I show you in the solution, in the code I give you, which is that to keep track of where you've been, use the stack, but you also color the back, each of these squares. And I go into how you do that on the video, but essentially, this class is all about solving mazes using, or this week is all about solving a maze using recursive backtracking, which is, well, backtracking because we're not really using recursion, but essentially you want to write a program that will find its way from here all the way to here. All right, questions from people who have questions from anyone. There's a write-up so there is a write-up, and in the write-up, I do give you the strategy on how to do it. Like, I do give you the generalized algorithm for doing this, so you will just have to translate that. There is extra credit available on this homework as well. If you go to the maze grid panel, which is where you're going to do most of your work, right? Solve maze is where you do your work. That's where I set the corners green and red to indicate the starting location and the stop location. There's this generate DFS maze. So if you notice right now, and as I discussed in the video, the maze is kind of, it doesn't look particularly like other mazes you may have seen, and that's because of the algorithm I used to generate the maze. Notice that this top row and this left column are all kind of empty, and that's because of the algorithm I used to generate the maze, which simply says either for each square remove either your north wall or your west wall, one of the two. Okay, and that just creates this kind of maze that will create a diagonal path to the end eventually, right? Which, if we're following, hey, I'm just going diagonal, and hey, there I am, right? So it just creates this kind of diagonal path through the maze. For extra credit, you can use def for search, which is what you use to solve. Well, you'll be using this def for search algorithm to solve a maze, which does this whole backtracking thing. And then you're going to do for extra credit, what you can do is you can use def for search to generate the maze. So actually, you can use the same way you'd be using to solve the maze, to generate the maze instead for extra credit. And for reference, the code I made to generate the maze, which I just simply called northwest maze because you're removing either the north wall or the west wall, that's over here. So there is extra credit opportunities available for that. All right. So if you have any questions on that or want to know how to get started on that, I'm more than happy to help with that. If you're working on the extra credit for Solitaire for last week, more than happy to help with that. I'm not sure if that will apply, if the extra credit will apply to the assignments or the exams. So I got to see how that works out. But extra credit's extra credit. So.